to distract me. Let's focus on chapter 4, probability. So my goal today is to do an intro to probability, which is 4.1, and then move on to more complicated probabilities, which is 4.2. So we'll see how things go. So let's start with the concept of probability is the statistical way of how do you put a number on how likely something is to happen. So you say, well, what do you mean? Well, we use the words in English language to try and convey that. We don't use numbers, typically. But, you know, if I went and said, it's very likely that sometime in the next 6 months, it's going to rain once in Washington, I think you would all agree that that is a very likely event, right? Things that are very likely happen a lot, right? Now, does it mean that it's going to rain every single day? No, I said it rains at least once, right? It rains one day, right? Could it be wrong? Well, there is a very, very slim chance that we hit the biggest drought that Washington's ever seen, and it starts today, right? It doesn't rain for 6 months, right? Could happen, but it's unlikely, right? So we talk about probabilities. We're actually using language like something is very likely to happen. It's very unlikely to happen. Have you ever heard the phrase 50-50? You know, it's a 50-50 chance it's going to rain tomorrow. Now, what you're saying there, it's an even chance, right? You know, half the time it rains tomorrow, half the time it doesn't rain tomorrow, those kind of terms. Well, we're going to try and put a number on those things. And that will allow us to make much more precise descriptions of how likely something is. So the definition of the probability of an event A. I'm going to use as my analogy this time rolling a dice. You know, if you take a dice and you roll it, it's got 6 numbers in it. So the probability of event A is described as the number of ways A can happen divided by the total number of possible events.
What is today's date?
So let's look at the probability then that I take a dice and that I roll the dice and I get an even number, right? So I roll the dice and a 2 or a 4 or a 6 happens, right? That's an even number. Well, how many ways can you get an even number on the dice? You could get 3. And how many things could happen when you roll a dice? There are 6 numbers. So the probability that you roll a dice and you get an even number ends up being the fraction of half. So let's start with the first convention. Probabilities are written in 3 versions. They're all the same thing. I could tell you that the probability that you get an even number when you roll a dice is a half, and that is correct. Probabilities are very often written as decimals. Would you agree that a half and 0.5 are the same number? And probabilities can be written as percentages. And you are going to find that as you go through this section 4.1, that they bounce between all 3 versions of how to write a probability. So you'll get questions where they tell you the probability is in percentages, but at the end, the probability that you're going to write down is a decimal or a fraction, right? So be aware that, you know, the box where you put your answer, look carefully to see whether it says, you know, how they want the answer, right? My first go-to would be try decimals before you try any of the other two, because you only get 3 shots, so you don't want to use them up, especially if the question says to 2 decimal places. That's a giveaway. But sometimes the answer will be a fraction, and that's fine. So 1/2 and 3/7 is totally fine. And I don't think any of the answers are percentages, at least none of the ones I looked at. Will you write down 50%? So go for a decimal, and if that don't work, go for a fraction would be my order. And we are good. So let's look a little bit further into this. Suppose I ask you for what's the probability that you choose a card Okay, now I guess you need to know a little bit about decks of cards. So if you're not totally aware of what a deck of cards look like, there are 52 cards in a normal deck. Throw away jokers, we don't use them. They get split into 4 things called suits. There are called clubs, diamonds, spades, and hearts. Do you know that diamonds are red and that the hearts are red and that clubs are black in colour and the spades are black in colour? That's the usual deck. Now, 13 of each, right? And don't they go from ace, which is 1, 2, 3, 10, and they finish with a thing called the jack, queen, and a king, right? So back to my probability here then. What's the probability that you choose one card and it's a club? Well, there are 13 clubs in a deck of cards. There are 52 cards I could have chosen. And so the probability is 1/4 or 0.25 or 25%. Right. Are we good? Now, I'm going to try and do all my answers from now on as decimals. And you will just bear in mind that although I might give the answer as a decimal, it could be a fraction or it could be a percentage, and it would be the same answer. And the reason I'm choosing decimals is for comparison. Suppose I had the probability some event, I'm calling it A, and then I want to compare it to another event, I'm going to call it B. And this guy is 3/17, and this guy is 4/52. And I wanted to know which one of those two was the most likely event. That would mean which one of these two had the biggest probability of happening. Would you agree that when you do probabilities as fractions, it's very difficult to compare if they're not the same denominator? So I'm going to round off to 2 decimal places, and the first one ends up being 0.18 to 2 decimal places, and the second one ends up being 0.08. Can you see it's now much easier to compare the 2 answers in that format? Are we good? So my usual convention then is that all probabilities are going to be converted to decimals, and if I need to, I'll round them off to 2 decimal places. Now, imagine that I have a line that represents all the possible probabilities in the world. And we're talking about as decimals, right? So I'm going to write out all, these are all the probabilities in the world written as decimals. What's the smallest probability you could ever get? And it has to be a positive number. Number of ways it can happen. divided by the total number of things that could happen. What's the smallest probability?
0.
0. If an event has a probability of 0, doesn't that really just mean in everyday language, it's never going to happen? The probability that a politician will never lie is 0, right? That kind of probability, right? The probability that I am going to be a billionaire by winning the lottery today is 0, because I won't be buying any lottery tickets today, for example. Now, what about at the other extreme? So this is, it's never going to happen, right? What's the biggest number as a decimal a probability could be?
100?
Well, 100%, yes. But as a decimal, what would that be?
1.0?
0. I'll just call it 1, right? And that, well, that represents, it will happen. It's guaranteed. What would that look like? What's, you know, if I said to you, what's the probability that I roll a dice and I get a number between 1 and 6, right? I get a number 1 to 6. The answer is yes, you are going to always get a number between 1 and 6. That is a guaranteed event, right? A probability of 1, right? Probability of 1. Anything that you know is guaranteed to happen, right? Something that is for certain. The probability that I am going to eat another Indian curry in the next 2 days is 1, because I am definitely going to be eating one very soon because I like them, right? The probability that someone in the universe is going to laugh at one of my jokes is 1, right? Somebody somewhere is going to do it. So if it's a guaranteed event, now right in the middle is 0.5. Right? Is it that it's just as likely to happen as it's not? It's a 50-50 situation. Oh, even. So you ever heard that phrase? Oh, it's an even chance of happening. Right? Things that are 50-50, right? It's just as likely to happen as not are in here. Now, as you travel along this scale, if you go this way, isn't that things become more and more likely? So something with a probability of 0.7 is more likely to happen than a probability of something that's 0.5. And if you travel in this direction towards these numbers, isn't things becoming less likely? So we have got now a way of describing how likely something is to happen. It's called the probability of it happening. And that always generates a decimal between 0 and 1. And the closer it is to 1, is it that the more likely it's going to be happening, and the less likely it is to 1, right? The less likely that it is to happen. So if I said that the probability that it's going to rain tomorrow is 0.3. Or human beings tend to like percentages when they do probability. I think your brain just works better. Isn't 0.3 the same thing as 30%? So what I'm saying is that there's a 30% chance that it's going to rain tomorrow. In fact, when you look up weather forecasts, or maybe the guy on the TV who tells you, don't they, at least sometimes, don't they tend to qualify their prediction by saying there's a 60% chance it's going to rain tomorrow? You know, if you look online in your weather, doesn't it give you a little, you ever notice it gives you little percentages of from 2 to 3 is a 20% chance of participation. Do you see that? What they're really telling you there is the probability that in that window of time, it will rain. And they get that by using probabilities. They're a little bit more sophisticated than ours because what they have is that they have computer models, right, which are basically big fancy computer programs. And what they do is they feed in information like the direction of the wind, the air temperature, you know, all the kind of things that weather stations tell them. It all gets fed into this computer. The computer has a model about how the weather works. And then it's basically the computer that pops back and tells them probability of rain or snow, or, you know, the temperature is going to reach at least 70 or anything else. And it will model, it will predict what the weather is going to be like in the future based on the information that it has today. Weather prediction is a little bit, what's the word I'm looking for? It's not a perfect science. Do you know that weather forecasts get things wrong? They get it right, or close to being right most of the time. But they don't always get it right, and that's because the weather is such an unpredictable thing. I'm going to stop for a second and mute everybody, because I'm sure they don't want us to hear their conversation. I'm going to add some people who turned up a few moments ago. So welcome to our latecomers. So is there any questions so far about, you know, what is a probability and some of the values that it takes, and how that big probabilities, things close to 1, mean it's going to be a really, an event that's really likely to happen? Okay, I am not working.
I do have a question.
Okay, yes, Lee.
Turning the probability into a decimal, do you always round by 2 places?
It depends on what they want. So when you read the homework question, it'll say to 2 to 3 decimal places. So if they say 3, do it 3. I've just decided arbitrarily to do it in 2. And the reason I'm doing 2 is it isn't a 2 decimal place decimal quite easy to turn into a percentage. No. So if I say it's 0.12, you can say, 12%. So it makes it visual in your brain a little bit easier to convert. Because as I said, human beings tend to like percentages when they're thinking of probabilities. You know, if I say something's got a 92% chance of happening, do you get a good picture of how that's probably going to happen more times than not? And if I say 0.92, it's the same thing, but isn't it a little bit harder just to visualize, I guess.
Okay.
Okay, so that's the rule. Whatever they tell you, you do it. But I'm going to do it to 2 because I can do that. So here's a question for you. I'm going to write down 3 probabilities. I'll call them A, B, and C. And this guy here is -0.5. This guy here is 1.2. And this guy here is 0.31. Only one of those 3 probabilities can exist. The other 2 are impossible. Which 2 are impossible values for a probability ever to be equal to?
Is it A and B?
Correct. What's wrong with A?
It's a negative?
Right? All negatives get thrown out. There's actually a question like that in the homework, I believe. Right? They give you some things and you know which ones don't work. What's wrong with B?
It's over 1?
Yes. Don't go for the hard things, right? Sometimes the question is what's in front of you, the obvious. Sometimes that's what the answer is. So remember we said probabilities have to be between 0 and 1, right? And any number that's negative will never be a probability. And any number bigger than 1 is, again, never going to be a real probability. So you can look at that situation. Now we're going to look at what's called a probability distribution. So imagine that you're doing some experiment or you're collecting information and there's only a finite number of things that can happen, right? And you've got the probability of each thing that could happen, right? That's called a probability distribution. So for instance, if we go back to doing the dice one, so you've got the number on the dice, and then you've got the probability. Then a dice could be a number 1, a 2, a 3, a 4, a 5, or a 6. This is going to be a very boring probability distribution because all the probabilities are going to be very similar to each other. For instance, what's the probability that I roll a dice and I get the number 4? Right? So it's probability that you roll and you get a 4. Well, how many ways do you get a 4 on a dice? There's only one 4 on the dice, right? How many things could happen in a dice? It's 1/6. And if we take this guy and we do a 1 divided by 6, that's about 0.17. Actually, I should have put it there. But isn't the probability of getting a 1, 2, 3, 4, 5, and 6 also the same? Would you agree that all those events happen at the same likelihood? And this is called a theoretical probability distribution because I didn't actually get a dice and roll it and figure out, oh, it was a 4 or it wasn't a 4, right? Or done anything like that. Then I just say, look, each number is just as likely to happen as any other number. There is one number 4. There are 6 numbers that could happen. The probability is 1/6, which as a decimal is that guy. Now, someone is playing a game in a casino and the guy's winning. You know, that game where you throw the dice and crap, I think it's called, right? The guy's winning an awful lot and you're not comfortable that he's actually got a fair dice. Because if it was a fair dice, wouldn't you get this kind of distribution? Wouldn't you get each number would happen just as likely as the others? But this guy seems to be getting an awful lot of 6s. Right, I'm going to have to go out and in here because somebody is asking something. Oh, okay. Someone answered it. That was cool. Thank you for doing that for me. Right, make that go away. So you get the dice off the guy and you do can't even spell, not empirical. You do an empirical probability distribution. The word empirical can be replaced by other words, but empirical is the one I like to use. So you could say the experimental probability distribution. Now, what happens in this case is that you get that dice and there's a 1, a 2, a 3, a 4, a 5, and a 6, right? And you roll the dice, I don't know, 100 times just to make life easy, right? And when you roll that dice, right, you record the following: 40, 12. I'm making my numbers kind of easy to deal with. That's 100 throws, right? Now, 40 out of 100. There's a guy here called the relative frequency. Can you remember relative frequency from histograms? Right. 12 out of 100 is 0.12. That's why I chose these numbers, so I didn't need too much. And this guy is 0.4. So to get the relative frequency, you take 12 and you divide it by the total amount of the data. In this case, I made it a nice number for calculations. Now, this is the empirical probability. This is the percentage, or in this case, the decimal number of times that this happened. Now, if you compare what the theoretical probability says should happen and what did happen, would you agree that there's quite a big discrepancy? Roughly, shouldn't 17% of the time be what percentage of any given number should happen if it was a nice dice and there was nothing weird about it, it wasn't a fixed loaded dice? Can you see here how big that is compared to what it should be theoretically? Wouldn't this be evidence that you could go to a court of law and say, look, this guy was cheating. He was using a loaded dice. Now, you probably won't convict somebody on 100 throws, but couldn't you do 1,000 throws or 10,000 throws? And if the same thing still happened, wouldn't you basically get evidence for it? You probably would actually just take the thing and stick it in an X-ray machine and you see the lead that they put on one side. That's how they cheat. Right. But you can imagine what you've got here is this is real data, and therefore it's empirical probabilities. And this here is theoretical, right? This is caused by us just looking at the situation and saying, this is what would happen in a perfect world.
Why does the empirical probability distribution use relative frequency rather than just frequency?
Well, you can't really compare these numbers to these, because if I did this 50 times or 200 times, wouldn't these numbers all change each time? So if you want to compare like with like, don't you really have to compare decimal version compared to decimal version? Does that make sense? So it's to make the comparisons equal. And relative frequency is, in fact, directly connected to the probability, isn't it? A relative frequency of 0.12 is basically saying this is happening 12% of the time. And therefore, this dice, you're only going to get a 1 12% of the time, instead of what you really should get, which is more closely to 17%. Now, this next thing is a little bit esoteric, but it's worth talking about. This is the probability distribution, right? For a normal perfect dice with nothing weird going on, right? Suppose I found a normal perfect dice, right? I bought it out the shop, there was nothing wrong with it. And I threw that dice, right, 100 times. Then roughly shouldn't 17 of them be each of these numbers? It doesn't quite make it as 101, but close enough. Do you know if I threw a dice 100 times, do you know the only thing I probably wouldn't get would be that? Because isn't there a thing called randomness, luck? Don't you just, have you ever played games where you roll the dice and your brother gets a 666? And you think, oh, that was lucky. And then he picks it up and he rolls it again and he gets a 666 the second time. Yeah, that doesn't happen that often, but it does happen, doesn't it? And can't that happen for some people a little bit more often than the theory says it should happen, right? And when that does happen, they say, you are a really lucky person. But that's just a word that we put on something that happened that probably shouldn't have happened, right? Do you know that the probability, back to lotteries, do you know the probability that you win the lottery, a typical lottery is 14 million to 1? There's calculations that you can base that on. But doesn't somebody win the lottery? Right. Now, 14 million to 1 is basically 1 over 14 million. Can you imagine how small that is? But somebody, you know, every few months at least, don't they win? So small probabilities don't mean it won't happen. Small probabilities just mean that it doesn't happen very often, right? That's all it means. And big probabilities don't mean that it's guaranteed. Could you imagine an event that says, oh, the probability it's going to rain tomorrow is 99%, right? The weather guy says 99% probability it rains tomorrow. Couldn't it happen that it doesn't rain tomorrow? In fact, one way of thinking of predictions that use probability is that if I say that it rains tomorrow, it has a probability of 99%. I'm saying that if I made that prediction 100 times, 99 of those 100 times I would be right, and one of those 100 times I would have got it wrong. Are we cool on the difference between empirical probabilities and probability distributions? So let's look at a table of collected data and use that to talk about probabilities. So let's have this class. I don't know how this is going to work or if it's going to work or not. 1, 2, 3. I may cheat here to make the data work. Okay, I'll put 5 in. Okay, so what we're going to ask you, and I'm going to have to go out of this to collect our data, is that we're going to get some empirical data. That means real data with real numbers, right? We're not doing it theoretical like throwing a dice. We're just going to collect some numbers, and from that we'll generate some probabilities later, right? So this question is, how many countries have you been to in the last year? Now, you're in America, so you already know that the guaranteed one, right? So we're taking that one for granted. Okay, so in the last year, has anybody been to America plus one more? Anybody been to 2 countries? I got 2 people, all right. Anybody been to 3 countries? 3 countries. Wow, cool. Anybody been to, Shay? Anybody been to 4 countries? Last but not least, anybody been to 5? Okay, then I don't need that data. And if there's somebody more, forget it. Okay, everybody else is left. So can I pretend to make numbers easier? I'm going to cheat. That adds up to 6. Can I pretend that there's 30 in the class? So 24 of you have only been to 1 country, right? Just to make the data. Now, this is empirical data, right? This is data that we have collected. Okay. Now, I can use it to get probabilities. So what's the probability? Sorry, Jenny?
We can't see what you're writing.
Oh, thank you. Right. There's our guy. We're not using that because, right, there we go. There's my data, right? Suppose I said to you, what's the probability I choose somebody at random and that it's been to 2 countries? Right? So this is empirical, right, based on our data. Well, 2 people out of a total of 30 that I could have picked, right? So if I just randomly said, Doris, how many, just out of curiosity, Doris, how many countries have you been to?
1.
Right, so you wouldn't have been it, right? I would have got it wrong. But how many times am I going to get it right? Well, 2 out of 30. Oh, by the way, I'm going to do this because some questions do want fractions. And when they want fractions, you're expected to simplify when possible. And now I'm going to do my answer, which is 0.07. So I have a 7% chance of picking somebody in this class and that they chose, they'd been to 2 countries this year, in the last year. Suppose I asked you this one. What's the probability that you've been to 3 or more countries? Now, the bottom's still 30. How many people in this class have been to 3 or more countries? I think I've
4.
seen, yeah, agreed. Agreed, which is 2 15s, which I believe is about, what, 14% of the time, not a surprise. Couldn't I ask questions like less than 2, between 2 and 3, and all sorts of combinations that belong in, you know, the usual English language? So do you see that this empirical data does allow us to do that? I can even ask a kind of weird one. What's the probability that I choose somebody from this class and they've not been to 2 countries, right? So it's different from 2. It can be anything you like. It's just not allowed to be 2. So there's 30 on the bottom. How many is not 2?
28.
Which ends up being that guy, which ends up being that guy, right? Now I want you to look at these 2 answers for a minute. The probability that you had been to 2 countries is what, 7%? The probability that you've not been to 2 countries is 93%. Do you know those 2 numbers are not random, they are connected to each other? What do you get if you add them together? You get 100, don't you? So if I said, look, I'm not even going to tell you this table. Here's a new table. The probability that you get 5, whatever that is, was 13%. What's the probability that it's not a 5?
87%?
Yeah. Oh, she
Agreed. 87% agreed. I mean, as a calculation, don't you just subtract the guy from 1 and you're done? Now, when you have 2 events, and they're typically written something like this, A, and then you add the probability that it's not A, the answer is always 1, isn't it? Or 100%. Does that relationship seem reasonable? Right? The chances I get a 5 and then the chances I don't get a 5 always add up to 100%, always add up to 1. So if I know the probability of something happening, don't I also know the probability of it not happening? So if I tell you the probability that it rains tomorrow is 0.15, then the probability that it's not raining, and you know in English we probably wouldn't say not raining, wouldn't we probably say dry, but we all know that means not raining, right? Wouldn't that be the other 0.85? Are we getting a little bit more comfortable with this number way of describing how likely something is to happen by giving a decimal value between 0 and 1? And that this decimal value can be calculated if we have a table like this, or we could do it theoretically like throwing a coin or picking a card, right? So let me show you a couple of card ones because they tend to be more interesting. They are theoretical, right? Because in normal cards, right, there's 52 cards, so we can say any one card is just as likely as any other, right? We're allowed to do that. So what's the probability that I choose a card from a deck of 52 and it's red? Well, the bottom number is 52. So if you know anything about cards, isn't there 13 red hearts and 13 red diamonds? And so I saw some of your lips move and you were saying 26. So as a decimal, Isn't that 0.5? What's the probability of getting a king? Well, there's still 52 on the bottom. And now you have to know a little bit more detail about how many kings are there in a normal deck of cards.
Four.
Four, right? King of Hearts. You know, there's a couple of cards. I mean, you could get a deck of cards and just count them if you get unsure about it. And that guy ends up being what, 1/13th. And I've done 1/13th before, I feel like, but I've forgotten what the answer is. 1 divided by 13. It's about 0.08, at least to 2 decimal places. Now here's, be careful. A red king. In a deck of 52 cards, how many red coloured kings are there?
2.
2. Josh, you're doing 2. I agree with you. And that guy ends up being 126, so I'm guessing it's about 4%, right? You comfortable about, you know, and I could, oh, I guess I could do this one. How many face cards there are? Well, you have to know a face card. So it's a jack, queen, or a king counts as a face card, right? When you get the cards, are little people's faces are on them, right? That's why they're called face cards. How many face cards are there?
So there'll be 20.
How many jacks are there?
4.
Queens
4.
and kings.
4.
That's it.
Maybe 16.
So are aces face cards?
Wow.
Ah,
Wow.
aces do not count as
12.
face cards, right? So that's maybe where you were coming from, right?
All right.
So there's only 12 of them, right? There's 4 jacks, 4 queens, and 4 kings. That probably was a little bit unfair because if you're not used to cards, you might not have counted it correctly. Right, so can you imagine that you could just continue with this process and do more and more complicated probabilities? Have you noticed that the thing about a face card question is, isn't the bottom number always 52? Because there's always 52 cards. And isn't the top one just a matter of counting correctly? You know, once I know what I'm looking for, make sure I only count those guys, right? Right, what I'd like to do now is go and have a look at some of the homework questions, just to get a feel for, where the heck are you? Here we are. And we'll start right off with question 2. Do you know I talked about the probability of something happening and then the probability of it not happening? Remember that? What I don't know if I mentioned is that it's called the complement. So A and its complement is not A. That's just the term that A is. So a newspaper states that the probability of rain today is 50%. What is the complement of the event rain today? And I guess it would be no rain today. Make sense? Now that you know what complement means. Now, what is the probability? Enter your answer to 2 decimal places. Good, because now they know they want a decimal. Can you see that in this case it's a bit of a shake? What is the not rain probability?
50%.
Yeah. It would have been much nicer if they'd said 40% rain, right? In which case 60% not rain, right? You see what I'm saying? One is 0.3, the other is 0.7. So that would be that one. We've covered this one, but I guess since it's here, what's the probability of an event A that is certain to occur? What number do you give to that probability?
100%.
Okay, and I'm going to assume that they want decimals unless otherwise. So what I'm just saying is, if you put in 100, it might say wrong. Not because you're wrong, because 100% is right, but they want the answers to be decimals, it looks like, which is fine, right? So always do the decimal, and if that doesn't work, then try the fraction, and if that doesn't work, then you can try your percentage. I don't think they use percentages in any of the answers. That's why I'm making that the last choice. On that same thing then, wouldn't an impossible event be 0 in everybody's world? Because 0% is also 0. Now, this fella called the law of large numbers. What that says is, if you take a probability of any event, right, and you perform an experiment. Remember the guy with the dice we thought was cheating, right? If you roll that dice lots and lots and lots of times, then the relative frequency that you get from your empirical data will eventually be the same numbers that you should have got if you had done it theoretically. So see, if you take a normal dice and you roll it in 1,000,000 times, shouldn't each one of the numbers come out about 1/6? And that's called the law of large numbers. And if there's something wrong with the dice, if it's fixed, shouldn't the answers come out as not those numbers, like the 40% dodgy dice one, right? Okay, I want to pause at this point because it's given me a clue to what we haven't done yet. I'm going to show you what a common mistake that people make when they're doing probabilities. Here's a theoretical situation. We have 2 coins, theoretically perfect coins. Now, when you're a perfect coin, isn't the probability that you get a head going to happen half the time? And isn't the probability that you're going to be a tail is also going to happen half the time? Would you agree? Theoretical probabilities, perfectly cool with that. Now, we're going to take 2 coins and throw them in the air. And here is the mistake that people make. You write down, so I want to know what's the probability that I get 2 heads, right? So I throw the 2 coins and I throw them together, right? Up in the air, they land, right? What's the probability I get 2 heads? This is the mistake people will make. They will say, there's 3 things that could happen. You could get 2 heads. That's one of the things that could happen, right? You could get 2 tails. That's the other thing that could happen. Or you could get 1 of each. That's the third thing that can happen. So since there's 3 things that can happen, there's 3 on the bottom. And how many of those 3 things are 2 heads? And the answer is, there's only 1 of those. And that comes out about 33%, right? Now that is actually wrong. And in the early days, side issue here, do you know probability came about from a rather unscrupulous history? It came about from gamblers. Gamblers were coming to mathematicians and saying, hey, there's this new game that you throw 2 coins in the air, and if you predict what's going to happen, you win. And if you don't, you lose. Can you give me an edge? Can you tell me, is there something going on in this situation that I should gamble this way and I'll win more than I lose? You know, that kind of thing, right? When you roll 2 dice, right, is it easier to get a total of 11 than it is to get a total of 10? Right? Which one should I gamble? The 10 or the 11? You know, those kind of questions. They come up with them. And that's kind of where probability started from. This is not correct. there's a thing that we call the sample space. It's just basically all the ways that something could happen. So let's go back to the coin situation. And this time I'm going to take note of that means the first is ahead and the second one was ahead. So imagine my coins were red and green, right? For some reason they get colored before, right? Couldn't I get a head and a tail? But isn't it also that I could get a tail and a head? Do you see they count as different events? You know, the red one was a head, the blue one was a tail. Right? The red one was a tail, the blue one was a head. You see, that's different. And then you finish with two tails. So the probability is now 4 on the bottom and 1 on the top. And that comes out as 0.25. Now, if I want to do a distribution, right, a probability distribution, and this one is theoretical, right, because I'm not really throwing coins. It would look something like this. Let's count it as number of heads. And then probability. Right, so you could get 0 heads. You could get 1 head, or you could get 2 heads. Would you agree if you throw 2 coins, that's the only things that could happen? Now, getting 0 heads, isn't that just the same thing as getting 2 tails? And that will happen 1/4 of the time. And getting 2 heads, we've already done that one, is also 1/4 of the time. I do not need to calculate that middle number. I know what that middle number is bound to be. What is that middle number going to be?
50?
Yeah, 0.5. Because in a real distribution, probability distribution table, shouldn't everything add up to 1? Because that means everybody, right? Now, back to this gambling game. The guy came and said, hey, we're playing this gambling game. You throw 2 coins in there, right? And if you get it right, you know, the guy gives you your money back and 50% more, right? Whatever it is, he gives you odds. And the mathematician looked at it and says, do you know what you should do? Always bet on one of each happening. Because aren't you going to win half the time? If you bet 2 tails, aren't you only going to win 1 in 4 times? If you bet 2 heads happening, aren't you only going to win 1 in 4 times? But if you bet one of each is going to happen, do you see you're going to win half the time? Now, can you imagine some very rich, drunk Victorians, and you've got a guy and you say, hey, I've got this little game. I'll let you throw the coin so you know I'm not cheating. And I'm going to bet £50 and you're going to bet £50, all right? And I'll let you pick which one you think's going to happen, and then I'll pick what I think's going to happen. And the drunk's going to probably pick one of these 3 at random, right? But isn't he probably just going to pick this one and this one as well? Do you know, in the long term, aren't I going to win? Because every time I've got a chance, aren't I going to pick one of each? And won't I win more often? And that guy will not even know he's being conned. Because won't he win sometimes? Because isn't that the art of gambling? To let them win sometimes. You know, if you gambled and every single time you went to the casino, you lost money, wouldn't you probably stop going after a few days or a few weeks or a few months, depending on how bad a gambler you are? But don't they let you win sometimes? And the casinos don't care that you win. It might seem strange, but they don't. Because see, the money that you win, wasn't that because 10 other people lost and you're just getting their money? You're not really getting the casino's money. They don't lose out of it. Casinos can't lose because, you know, they design the probabilities and the payouts so that they always come up on top. So it's, and I still like casinos regardless. So 3 coins. Let's do the sample space. Problem with the sample space is how many are there, right? So you got to know how many there are so that you know to stop when you found them all. So imagine that these 3 little brackety things with dots in them represented the things that could happen when you throw 3 coins. How many things could happen in the first coin? Well, isn't there a head or a tail? So that's 2 things. How many in the second? There's 2. And how many in the third? There's 2. Do you know that means then that there are 8 different things that can happen when you throw 3 coins? So suppose the gambling game's got a little bit more complex. You now have 3 coins, right? And you take them and you've got them in a cup and you throw them in the air and they land on a table and everybody cheers. Hopefully you've bet on the right event. You're only allowed to bet on one event. How many heads do you think would be the best bet? To bet on just 1 head happening, 2 heads happening, 3 heads happening. What do you think is going to be the largest bet? Or no heads happening, I guess. You're gambling. Would you want to
1?
gamble? You're going to go 1 head, right? You got 1 head. That's a good answer. We'll keep it. Let's find out. Now there are 8 things. I am going to start by creating the sample space. Because I need to know how many things can happen, because when I do my probability of whatever I decide to look for, isn't it going to be over 8? Because I know there's 8 things. But then don't I need to know how many ways exactly 1 head happens, right? So I got to know all the things that could happen, and then from that list of 8, I'm only going to pick the ones that have 1 head. Now, there are 2 ways to do this. The first way is not very suitable. You just randomly write down things until you run out of ideas. So you just go tails, heads, 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 tails, 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 you know, and so on. You'll be able to get 3, 4, 5 of them pretty quickly. Won't you have to struggle over maybe the next 2? And then won't there be 1 left over, and for the life of you, you can't figure out who it is? You know there's 8, but right now you've only got 7. Do you see that kind of hit and miss is probably going to cost you more time in the long run? It looks good at the beginning because you write down really fast, right? Because you've got a lot of, you know, random choices at work. But isn't there it's going to be hard towards the end. So what I suggest is that you do it the second way. And the second way is just have a systematic way of approaching. So I'll start with 3 heads. That's a good start. And then I'm going to do 2 heads and a tail. Now, do you see that I've been quite systematic about it? The tail goes there, the tail goes there, and then the tail goes there. Do you see that means I've covered all 3 possibilities, and I know I don't need to look for any more 2 heads and a tail, right? Now, what do you think my next combination is going to be? Okay, a head and 2 tails. Agreed? So a head and 2 tails, a head and 2 tails, a head and 2 tails. Do you notice that I've already got 7 of my sample space? And there's only 1 left. Who's the last combination that's not there?
Tail, tail, tail.
Right. Do you see that the way I approached that question made it a little bit more systematic? It gave you a way of figuring out what to do rather than just randomly writing them in as they come to your head. How many of those 8 things end up being just 1 head? Obviously, 1 head means there's 2 tails, right? Because there's 3 coins there. Well, 1 head, would you agree that's 1 of them? Would you agree that's 1 head? And you agree that's 1 head. So what's that? 3 out of 8? And 3 divided by 8 is about, I'll break my own rules here, 37.5%. Agreed? Now, let's do a probability distribution for this fella. Number of heads, probability. 0, 1, 2 heads, and 3 heads. And I'm going to just tell you the answers to some of these questions just for speed. But do you know the chances that you get no heads? Isn't that 3 tails in? And that happens 1 out of 8 turns. And let's do 1 divided by 8. And that happens 0.125. That happens 0.125. This happens 0.375. And actually, so does this happen. Do you see the probability distribution then prefers the middle numbers, 1 head or 2 heads? Aren't they going to happen roughly 3 times more often than getting no heads at all or getting all of them being heads? Do you see the distribution is not equally balanced, right? Some things happen more often than others. Now, in a gambling world, that's important because a lot of people who don't really understand gambling think that all 4 things are just as likely to happen as any of the other 4 things. And you see, with that misinterpretation of what's going on, won't you miss out on gambling on more likely events and keeping away from the least likely events? So if nothing else, I'm telling you how to gamble well. Now, a side issue, and I know the book doesn't tell you this, but it is such a cool thing, I want to show you. Monty, I think it's I. Monty has an I or a Y in it. Don't know. It's called the Monte Carlo fallacy. I think there's an E-Y in there. It's a common mistake by some gamblers. It originated a way back. One of the first casinos in the world was a place called Monte Carlo, which I believe is in the south of France. I haven't been there. I've been to the south of France, but I haven't been to Monte Carlo. By the way, beautiful place, south of France. If you ever get a chance, go there. Extortionately expensive. Anyway, back to my question. Monte Carlo fallacy. In a casino, there's a game, there's lots of games, but there's this particular game called roulette. And if you don't know roulette, you don't need to know too much about it. But basically, there's a big circle with wheels on it. You've seen it in the movie, you like the James Bond movies. They like roulette games in his movies, right? And the ball lands on a number, and the numbers are red, black. You know, half there's half the numbers roughly are red, half are black, and then they have a green 0 just to catch you out. And the green 0 is the odds. So can we pretend that there's a person that gambles, and one of the common gambles is you bet on red. And if you bet on red and you win, you get double your money. And basically, half of that is your money anyway, right? So if you bet $10 on a red number and a red number happens, the casino gives you back 20, but 10 of it is yours, right? But you double your money. It's a good bet. It's probably one of the best bets. If you ever go to your casino and you want your money to last a really long time, and they give you free drink, which they do in Vegas, go to the roulette table and just bet red. It's a boring game, but just bet $10 on red, and you'll last forever and a day. You'll still lose your money, but it'll last a long time. And you get free drink. So if you drink a lot and you bet small, you might actually come out up on the deal. And if you're not 21, ignore that advice right now. No drinking, no gambling, no Vegas, right? But once you're 21, you can do it, okay? So back to this one. It's called the Monte Carlo fallacy. I wonder, can you imagine they roll the roulette wheel? And it does happen. 6 times in a row, a red number appears. Now, the people who are sitting or standing round the roulette table, a lot of them, the Monte Carlo fallacy kicks in. It means it's a lie. They think one of two things, both of which are lies. One group says, the Reds are hot tonight. I'm going to bet red. The other group, hey, it's about time a black turned up, right? They got to happen half the time, right? Half red, half black. It's time for the black to come up. And they bet black. Both of those people are wrong. They're making the assumption that the red is more likely to happen than not, and that the black is more likely to happen or not. When you spin that little ball round a roulette table, isn't the chance that it's a black or a red half the time? And doesn't that little roulette ball not know that it's just done 6 reds in a row? Right? Isn't it still going to land on the red half the time or the black half the time? So the Monte Carlo fallacy is people think that probability helps you to predict a random event when it's not really doing that. Isn't it just telling you that the next one could be a red 50% of the time and the next one could be a black 50% of the time? And by doing that, you're really looking at probability the wrong way, right? Analogy. Can you imagine we lived in a place like we do, and the probability that it rains on any given day is 25% of the time, right? See if it rains 7 days in a row. What's the chances that the 8th day it rains? You know, it's still 25% of the time. The fact that it's rained 7 days in a row does not change the next event, because the next event is independent of what happens in the past. If you think about the ball going round, for this to be true, wouldn't that little ball have to know that it's ran 6 previous lives and it landed on a red, and now its goal in life is to be red again? So as you swing that little ball, it's got a mind of its own and it tries to jump into the red numbers. I mean, doesn't that sound stupid? I mean, it sounds like the thing's alive, right? It's got a goal in life. Probabilities have no goal in life, right? They just do what they do randomly every single time. So it's called the Monte Carlo fallacy. So if you do gamble and you're at a roulette table and a lot of reds happen, doesn't matter. The next one could be red or black, just as likely as any other time. Any questions about the Monte Carlo fallacy or anything that we've done? Are we comfortable? Right, now that allows me to go back to the homework, because I had a guy there that I looked at and I suddenly realized, as we do, that I hadn't done them. Right, so here is a family of 4 children. List the equally likely events. Okay. Oh, oops. These are the equally likely events. The question's a little bit different. I should have read it. List the equally likely events for 4 children from oldest to youngest. M be a boy, female. Now, equally likely events. See that one? 2 males and 2 females, right? You see that one there? Do you know any combination of 2 males and 2 females is going to be equally likely? Doesn't matter if the first 2 were males and the last 2. So based on that, I'm going to pick that one, that one, that one, and that one. Would you agree that those all represent different ways in which 2 males and 2 females get born? And the order in probability doesn't matter, right? Doesn't matter if it's a red and then a blue, or a black and then a red, they all count. If I haven't missed any, that would be the correct answer. So let me take these guys off and let's choose a different one. Let's suppose I decided to pick that one, because I might. In that list, I don't know, it's kind of small, so you might not be able to read it, but hopefully some of you can. Can you give me any other combination that would be the same probability as 3 females and finishing with a male? I can see at least one. Can you see it?
Is it the 3 males and 1 female?
5 from the bottom.
Or
There's one there, right? And there's one there, right? Would you agree that they're the same event? And any others in there that I missed? Would
are
you
we
agree
just
that's-
looking at the? Oh, sorry. Are we
Well,
just
the
looking at the
second-
probability?
Yeah. So that could be 3 females, 3 males and a female as well. Wouldn't that also be equal?
So, right. So it should be like on the second from the bottom. There should be 3 males and 1 female. That should
Yeah.
count too.
And so should that one count as well? Now, 3 females and a male and 3 males and a female are different events, but don't they have the same probability? Right. So that's a good question. I like that question. I'm not sure if it's programmed well enough to do what we just did. I hope it is. Okay, question 7. Hopefully a nice easy question because we've covered it. Why can't negative 0.41 be a probability?
They don't exist, right?
Yeah, but you've got 3 choices. Which one of those sentences is it don't exist?
Must be between 0 and 1.
Yeah. So yeah, I mean, if the choice had been they don't exist, I would have picked that circle as well, but only from the choices that they've got. In fact, looking at some of these, what's wrong with 120% as a probability?
Should be a probability between 0 and 1.
Right, so it's that answer again, right? And the last one is, can this probability, 0.56, can that be a probability?
Yes.
Yeah, but they give 2 yeses. Yes, it's a number between 0 and 1, and yes, it's a number between 0.5 and 1. So which one of them is a better answer to the why it's a yes?
Would it be the 0.5?
No, actually.
Oh. Okay.
0 to 1 is what all probability should be. Can't you be a probability and not be between 0.5 and 1, right?
That's true.
Right. Okay, 0.56 is, but 0.46 isn't, and that's still a probability. So that's why that third dot would be, in my case, the third dot. Right. I didn't know anybody. Yeah, people can. I take that back. I was going to say I didn't think anybody could wiggle their ears, but actually some people can. I just can't. Can you wiggle your ears? So you use students in your statistics class or a group of friends to estimate it. This is going to be the empirical probability, right? Where you do a little experiment and you get an answer and that's your best guess, right? Your best guesstimate. And you're going to do it to estimate the percentage of people who can wiggle your ears. How can your results be thought of as an estimate for the probability that person choosing the drum? Well, wouldn't the resultant relative frequency can be used as an estimate? Right. 5 out of my 20 friends can wiggle their ears, so that's what 25% of Americans could, right? I'm just nosy. Can anybody here wiggle their ears? God, yeah, I thought so. I think that's a bit. Oh, Joshua, you can do it. Well done. Do you have a muscle that makes it happen? Because when I try and wiggle my ears, I can't feel anything to wiggle with, if you follow me, right? Is there a trick to it, or you just were born to be able to do that? Oh, Joshua may not have audio. Okay,
Yeah,
we'll
you
leave
just
him
said
at that.
born.
It's a what?
Just said it if he was born with it.
Oh, yeah. You know, they do some weird things. I'm distracting myself, but I can. Do you know that your belly button can be an innie or an outie? And you're just born with it. There are lots of weird variations in the human body. What's the other one? Do you know you can be left-handed or right-handed or ambidextrous? So in that case, there's a 3. Do you know in the human race, right-handed is much stronger, i.e. there's a bigger percentage of right-handed people in the world. And then I'm trying to remember, I seen it in a social science article once. Somebody did it. I mean, how do they know? Well, they didn't go through the world. They just did a sample of people, and the averages tend to come out about the same. So it's not genetic in the sense that Chinese people are more or left-handed or right-handed than European people or whatever. It's pretty much universal, regardless of your race. And right-handed is the strongest. Left-handed is next, and ambidextrous is the rarest. It's very hard. A very small percentage of the population are ambidextrous. And my dad was really weird. Not me, and I think I know the reason behind it. My dad was right-handed, right? He, you know, if you he ate with his right hand, he wrote with his right hand. You know when you're right-handed, right? You can tell. But my dad was left-footed. When he played football, soccer, my dad kicked better with his left foot than his right foot. Now, there's 2 possibilities for that. There might be a fourth category. You know, left-handed, right-handed, ambidextrous, right? You're equal, right? There might be a fourth category where you can be right-handed and left-footed, right? In which case my dad was in a very, very, very small subgroup of the human race. What I think happened is less interesting. In Britain and probably in America, you weren't allowed to be left-handed when you were in school. So when you started as a little kiddie at 5 and you picked up your crayon with your left hand to draw pictures, they would physically take it out and put it in your right hand and tell you things like grown-ups use their right hand to draw, right? And they would force
What
you
year
to.
was that?
My dad was born in 1916.
Wow.
So in the 20s, they forced you when you were a child to use your right hand, right?
Yeah.
So I think what happened is that when my dad was even younger than he can remember, he was forced to write with his right hand, and therefore he became a forced right-handed person. Now, in today's world, if your child is left-handed, don't they just go with the flow?
Mine didn't.
What, your school forced them to be right-handed?
Well, so somebody, when I was in 1st grade, they were trying to teach me to do right-handed, and I was actually left-handed. And now I do kind of fudge a little bit on my on my words sometimes. So I'm like, I might be a little dyslexic because of that, but we'll see.
So, is that true? Anybody here left-handed? Just sharing. Anybody
I
else?
write right-handed, but I can bat left and right-handed and pitch left and right-handed.
So you're pretty close to being ambidextrous then, Jennifer, right?
Yeah, I just can't write like writing, but any sport, I can do it.
Do you think you might have been left-handed and they kind of forced you to be right-handed when you were really young?
I think because I'm first generation to be born in America. My family came from Norway. So I think because in a lot of other countries, they force you, like you said, and still to this day, they're forced to, right-handed. You're considered abnormal if you're left-handed. So it could have been, I don't know, I don't know for sure.
It's interesting that the history behind it. Anybody else here left-handed? That shows you it must be a pretty rare event. At least nobody wants to share. got to get this out of my head. It's not a joke. It's a true story. In Scotland, we have a name for left-handed people. They're called Corrie-handed. Right, Corrie-handed. That's how you pronounce it. Handed means handed, right? So it's like saying, and I thought, and I was wrong, so that's what I'm going to share with you. I thought Corrie was just a Gaelic word for left. So if somebody said Corrie-handed, you were just saying left-handed, right? That's what I thought it meant. And then I was with my wife, and we were on, I think I read it. If I didn't read it, we were on a bus that took us around. And they were taking us around Edinburgh. And Edinburgh, one of the clans that lived in the Edinburgh area were the Kerrs. And the Kerrs were interesting in that, you know that if you're left-handed, there's a higher percentage of your children going to be left-handed because there's a genetic component to being left-handed, right? So if left-handed parents tend to have, if both parents are left-handed, there's a higher percentage of left-handed children because of that. Well, the Kerrs were very left-handed. As a clan, there was an awful lot of left-handed people in it. And some of the advantages stroke disadvantages of left-handed. Can you imagine you fight with a sword and a shield? Now, most people, sword in right hand, shield in left hand. The Kerrs, because of where they were, shield right hand, sword left hand. The equivalent is, do you know when a left-handed boxer tries to fight a right-handed boxer, the left-handed boxer is at an advantage? Because the left-handed boxer is used to fighting right-handed people, but right-handed people are not used to fighting left-handed boxers. So the Kerrs had a big advantage in battles because you're normally fighting a guy shield against their sword, sword against their shield, but then you got this guy, hey, what's going on? And before you knew it, you get stabbed. And that wasn't good for you. Well, what they done to implement that is, in their building, in their castle in Edinburgh, their house at least, they built a spiral staircase, but they built a spiral staircase for a left-handed person. So that when you were attacking their building and you were coming up the stairs, you were coming up the stairs with your sword and unprotected side open. And the Kerrs would be at the top, protected. And so they were at an even bigger advantage. So what happened is that people would say when you were left-handed, they would say you were Kerr-handed. But the way that Kerr-handed got kind of corrupted was to say you were Corrie-handed, you were Kerry-handed, you were Corrie-handed. See the cool things you learn in our class? Left-handed.
I am ambidextrous.
You are ambidextrous. That is a cool thing to be. You're the rarest group of all the groups. So it's good to be rare, right? Now, I'm just zooming through the last of these questions and then we'll move on. So I'm looking at 11. When do creative people get their best ideas? Oh, interesting little table. It's empirical, right? They just asked some people. They asked a lot of people. I don't know how many, I guess a lot. Oh, 966 of them. I wish they'd done 1,000, it would have made the calculations easier, but never mind. And 294 did it then. 120 had their best ideas during this time. 300 at that time. And 239 at that time. Now, assuming that the time now can to the left and all the times, blah, blah, that just makes it easy to count. Find the probabilities of these things. Essentially, you're going to look at these. So if I took the top one, the 6 a.m. to 12 o'clock, 294 creative people said that was the best time for them personally to come up with a good idea. And it's about 0.304 according to me. You see how that would be calculated, right? Now, if you call that 30% of the time, right? Let's choose this one here. I like this one, 313. It's definitely the biggest. I just want to find out what that looks like as a number. And that's 0.324. So on this raw data, it does look like creative people are more creative, not during the workday. I guess 12 to 6 isn't quite the workday, but you see they don't tend to get their best ideas when they're in their office answering their emails and, you know, talking to their managers and things like that. It looks like they get their best ideas after their workday is finished, before they go to bed. You know, 6 to 12, that's kind of, I'm finished with my job, right? I'm back home, I'm watching TV, and then a cool idea comes into my head. Interesting though. Now, it says, do these probabilities, because these 4 guys, it says, do they add up to 1? They theoretically, shouldn't they add up to 1, right? Because that's everything. If you add the 4 up, they should add up to 1. Why might they not add up to 1? Why might they add up to 0.999 or 1.02 or something? How could that happen?
Maybe one person didn't get to answer, or
It's a little bit to do with the rounding off rather than that.
oh yeah, that's true.
Couldn't you just have some decimals where every single one of them get rounded up? Can you imagine? When you round something up, aren't you adding a little bit more than's really there? And if you did it to all 4 of them, wouldn't you end up with an answer bigger than 1? Couldn't you have a situation where 3 of them get rounded down and only 1 get rounded up? Well, when you added that up, couldn't you get an answer a little bit less than? So when you're doing empirical probabilities, theoretically at least, if you add them up, you should get 1. But because you're introducing some rounding off error, it's okay to be 0.998 or 1.02. But see if you add them up and you get 1.7, you're wrong, right? You're just wrong. 1.7 isn't rounding off errors, right? Isn't 1.7 I've screwed up somewhere? And isn't 0.599 also guaranteed to be wrong? So yeah, they should add up to 1, but they don't always quite do it because they're rounding off. Right, they said, what is the sample space in this problem? Isn't it in fact the entire day? If you put all of it together, that's the sample space. Okay, let's look at 13 then. John runs a computer software store. Yesterday he counted 139 people who walked into the store. So I'm writing that down. 139 walked in. Okay. Oh no. 139 walked by. So he watched them and they walked by the window. Of that 139, 56 walked in. That's good. Of that 56, 24 bought something. And now we have some probabilities that we need to calculate. And the first one is the only one I'm going to do. Find the probability that a person who walked into the store who walked by the store enters the store. So walked in. Okay. How many people walked by in that story? How many people walked by? Some walked in, some didn't. How many people walked by?
139.
Okay. How many people actually walked in?
56.
So your answer is 56 out of 139. Now, what's different about this question is that the bottom number will change depending on how they phrase that question. Now, in this case here, 139 people walked by, 56 walked in. So the probability of that event happening is 56 out of 139. Now, do you know that 25 people bought something? I could ask that question in two different ways, right? What's the probability that you bought something given that you had walked by the shop? Well, wouldn't that be 25 people out of 139, right? What's the chance that you bought something given that you were one of the people that walked by? And the answer there would be 25 on the top out of 139. But couldn't I also have said, what's the probability that you bought something given that you were one of the people who actually came in? So that would be 25 out of 56. Now, do you see those two percentages are different? Now, if you were a shopkeeper and you were collecting that data, those two numbers are quite important. And isn't the first one basically a percentage of the total number of people that you contacted? So forget about walking by. Think of this as being advertised. People who saw my advert, right? How many people online bought something, right? So you can keep a little ticker. You know that the person's seen your advert, right? They have a little thing that they keep tabs on that, right? And then the second figure is how many people, right? In this case, would buy something. And those two numbers are different. Could you imagine a shop where lots of people walk by? But if nobody comes in and buys something, won't you go bust? So don't you want a high percentage of foot traffic to not walk by, but walk by and then come in, right? So if your shop is in the middle of the main street, won't you get a large number of people walking by your shop? Because you're in a popular traffic area. Isn't that why rentals for high traffic areas are higher than rentals for side streets? Because the people who own those buildings know that one of the ways in which you make money is by having potential customers, and potential customers transfer into people who are likely to walk by your shop. Now, the second figure is more up to the guy who has the business. If you do a really good job, won't you encourage a lot of people to come in and hopefully buy stuff? And how do they do that? Sales, 50% off. Buy two, get one free. We've now got the brand new gizmo thing that you're all wanting to get. You know, the kind of advertising where you get people to come in. Free samples. You know, techniques to get you in, because one of the techniques is if you come in, then won't you have a better chance of selling something to someone than if they just keep walking by, right? You're not going to sell anything from those. So those are the kind of strategies that businesses. So you want the probabilities to be as high as possible, because that is going to make your life, as a business owner at least, more profitable. Right, let's check any chats here. Okay, so let's move. Really just to finish off here, because I should check my time, because I want to be 25. Yeah, I got, no. According to my watch, I've got 7 minutes. So that gives us enough time to move on to our second section, 4.2, which is going to be complex probabilities. So let's give you some examples of some complex probabilities. The word or. You wouldn't think there'd be a lot of problems with the word or. There is. There are two kinds of or in the world. There's the inclusive or and the exclusive or. And in the English language, we are quite precise about what or means. But in statistics, the or we use is called the inclusive or. I'll give you an idea of what I mean. If you say to a child, you can have cake or you can have ice cream. That's the exclusive or. When you say that, if it's you, if your mum says, look, you can only have cake or you can have ice cream, doesn't that mean you can only have cake and that's it? Or you can only have ice cream and that's it? But you're not allowed both. In math, when we say that, we don't mean the exclusive or, we mean the inclusive or. That means you can have cake, you can have ice cream, and you can have both. All three possibilities are allowed. So be careful when you see the word or in a probability question. We are talking about this version of or. Now, if anybody has done computing, you will know what I'm getting at when I talk about an inclusive and an exclusive or, because I believe in computing, don't you have that same kind of version of or when you do truth tables and so on? Does anybody want to back me up on that? Just to say, yes, I've heard that you can have two kinds of or. Now, what makes this a complex probability? Here we go. What's the probability that you pick one card from a deck of cards and it's a king or a red? Now, can you imagine that this bubble represents all those cards that we're talking about? So there are 52 I could pick. Let's find out how many out there goes on the top. Well, would you agree that there are 13, would you agree that there are 4 kings? How many red cards are there?
26.
Yeah. 13 red hearts and 13 red diamonds. Now, this is the problem. 4 kings, 26 reds. The answer should be 30 out of 52. It's not.
You have to subtract the king.
You have to subtract the 2 kings, don't you? The 2 red kings, for want of a better word. And can you see then that the correct answer is a little bit more complicated to calculate? Does that make sense? That what's the chance that you take it? If you took an entire deck of 52 cards and you put in this pile here all the kings and all the red cards, do you know there would only be 28 cards there? And you might say, well, there's 26 red, which they totally are. But it would look something like this. There'd be 2 black kings and 26 reds. You can't count the king of hearts twice, right? That's not right, is it? Okay, you got it, Doris? Light bulb? Got it, okay. So how does that look like when you try and write it in a general way? Well, it looks like this. There's a formula. A or B, right? Red cards or kings, right? It's the probability of A plus the probability of B, take away the probability, let me start again, I need more room. Probability of A or B, it's the probability of A plus the probability of B, subtract the probability of both. Now, let's go to this question here and show you what that would look like. The probability that you get a king or a red. That becomes the probability that you get a king plus the probability that you get a red, take away the probability that you get both. Right. Totally independent of each other. Aren't there 4 kings in a deck? So the probability that you just get a king, nothing else to think about, just a king, won't that be 4 out of 52? Now again, forget about everything around it. What about getting a red? Well, aren't there 26 reds? Now, how many are both? Isn't that another way of saying how many are red kings? So how many red kings are there? 2. Now, if you stick that together, can you see where the 4 plus 26 take away 2 is now coming from? Now, that's what it looks like. It's 3 separate things, because typically, won't these 3 things all share the same common denominator? Right, so when you put them together, it's like one big calculation. And just to make things a little bit harder, right now, just to start with, I'm calling that both. But that's not the way you're going to see it in a textbook. Has anybody seen that funny little upside down curved guy? Anybody seen that guy? He's called intersection. That's what they mean when they say both, right? So A intersection B means both, right? So if you want to just turn that into the word both in your head, it'll make it a little bit easier to calculate. I think the word both is easy to, make sense of. What would this mean? A different story. Who knows what A, B, and C is? But in English, wouldn't the probability of A intersection B intersection C mean only those things where all 3 things are true? So could you imagine A was male, B was math, and C was Bremerton? Then wouldn't this represent male math people who live in Bremerton? Right? It'd be all 3 things at once. And that's what both represents. Right, for the last few moments,